Hi everyone, welcome to lecture 48 in electronic devices course. From this lecture onwards, we will study the operation of bipolar junction transistor. And we have seen in the previous lecture that transistor can have different modes of operations like active mode, cutoff mode, saturation mode or reverse active mode, etc. So for each operation, I will make one video lecture. So that's why I have given the number 48A. Right? For the next operation, I will give 48B and so on. So first we will discuss what we have seen in the previous lecture. So in the lecture 47, I introduced the bipolar junction transistor. So first we have seen applications of 3-terminal devices. So it can be used as an amplifier, it can be used in digital circuits designs, memory circuits designs, etc. Then BJT was invented in 1947 December by 3 great scientists. So William Shockley, John Bardeen and Walter Brattain. And we have seen two effects, that is the effect of asymmetric doping. That is when we make one side heavily doped, another side normal doping. That is, if we make a heavily doped P, then it will be P plus N. If I make a heavily doped N, then it will be N plus P. So for this type of PN junction, the current will be dominated by the holes. Here the current will be dominated by the electrons. So this effect we have seen in the lecture 47. Then we have seen PN junction under reverse bias. So in reverse bias we know the depletion region is large. When we inject some electrons or holes in this depletion region, they will be collected by the N side if we inject electrons. If we inject holes, they will be collected by the holes due to this electric field. Then we have seen the physical structure of bipolar junction transistor. So in BJT we will have 3 doped regions like P plus N P, or we can say PNP region. So it can be called as PNP transistor, or we can have NPN transistor. And the 3 terminals or 3 regions are called emitter region, base region, collector region. And we have seen emitter will be heavily doped, base will be lightly doped and collector will be moderately doped. And depending on the area, or we can say size wise, base should be very thin, collector should be large and emitter should be moderate. Right, these are we have seen. If you are having any doubt, you can post a comment also. And next we have seen symbols for BJT. So this is the symbol for NPN transistor and this is the symbol for PNP transistors. And this arrow should be given to the emitter only. And why the arrow should be given, out of the emitter means whenever PN junction is forward bias, current will flow from P to N. So this is about the active mode, that also we have seen. Similarly PNP also, P to N current will flow when emitter base junction is forward bias. Then we have seen modes of operation of BJT. We will have 4 different modes of operations like active region. In active region, emitter base junction should be forward bias, collector base junction should be reverse bias. So emitter base, so this is the emitter base junction and this is the collector base junction. So when we make this junction forward bias, this junction reverse bias, it will be in active mode. When we make 2 junctions reverse bias, it will be in cutoff mode. When we make 2 junctions forward bias, it will be saturation region or saturation mode. When we make opposite of this active mode, like emitter base junction reverse bias, collector base junction forward bias, then it will be called as inverse active. So we need to see why it is called active region under these conditions. So we will go in detail analysis of these operations one by one. Right? That is about the introduction to bipolar junction transistor. So in this lecture, our objective is to study the behavior of open circuited transistor. First we will understand what is the meaning of open circuited transistor. When we take any transistor like NPN transistor or PNP transistor, when we don't apply any external voltages, then we can say it is open circuited transistor. The same concept we have discussed when we discussed the PN junction. That is PN junction under open circuit. That means when we take a PN junction and when we don't apply any voltage, then we can say PN junction under open circuit. Then what happens when we don't apply anything? That we have seen for PN junction. Similarly we will see for transistor. So in this we have to discuss what is the built-in potential across each junction and what is the minority carrier concentrations, right, at each junction. So for that I will take 2 transistors. First we will see for PNP transistor, then we will see for NPN transistor. So this is a PNP transistor. So to indicate emitter is heavily doped, I have given the P plus. N is the base region in PNP transistor, and this P is the collector. And remember always, whenever we are drawing the physical structure of a transistor, that to BJT, collector width should be always large compared to base and emitter. And base should be very thin, emitter should be in between these two, and emitter should be heavily doped, that is already known, and this should be lightly doped, this is moderately doped. Similar we can apply for NPN transistor also. Heavily doped, lightly doped, moderately doped. Large width, very thin, moderate. Now in a P type, that is heavily doped, who will be there? Holes, right? The majority carriers in P type semiconductor are holes. How to represent hole means, simply we can represent plus sign. So if it is a hole, that means it's a positively charged particle. So plus electron means negatively charged particle. We can represent like this also, very simple way. So it is having holes. Heavily doped means so many number of holes will be there, right? N type, who are the majority carriers? Electrons, but it is lightly doped and it is very thin, so number of electrons will be small. And this is a moderately doped, again P type, so it can have holes, right? This is the representation. Another representation is also there. We can represent like a negative and hole. What is this meaning is, whenever it accepts any electron, it will become negative ion. Suppose, and how to represent electron? Positive sign and dot. Whenever it loses electron, it will become positive ion. So this concept we have seen when we discussed the PN junction. So this is the hole representation, this is the electron representation. Either in this way or in this way we can represent hole. When we represent like this, it will be very easy to understand the concept of depletion region or built-in potential, right? So that's why I'm drawing in a different way, something like this. So again it is a PNP transistor only. So P is heavily doped, so many number of holes, and lightly doped, less number of electrons. This is moderately doped, so less number of holes compared to the emitter. So it is represented by C, minus and hole. Whenever it accepts the electron, it will become negative ion. Whenever it is losing the electron, it will become positive ion. Now we'll see what is the meaning of open circuited. So when we don't connect any external voltages or supply, then we can say it is under open circuited, similar to the PN junction. Now here, how many junctions are there? 2 junctions. So this is a PN or P plus N junction. So I'm naming as JE, emitter base junction, and this junction we can give as JC, collector base junction. So emitter base collector. So there are 2 junctions. So we will deal with 1 junction at a time. So when we consider this junction, that is emitter base junction, it will be looking like a simple PN junction, right? So we'll deal with 1 PN junction at a time. So when we consider this PN junction and when we don't apply any voltage, what happens? That we know that in P type majorities are holes and minorities are electrons. So there will be some electrons. In this, majority are electrons, minorities are holes. So there is a non-uniform concentration is existing. So what happens? Diffusion will take place. So the holes will move from this emitter region to base region, and electrons will move from base region to emitter region. Then whenever it is losing the electron, it will become positive ion. Whenever it is losing the or accepting the electron, it will become negative ion. So after some time, the junction will become what? Something like this. And we know whenever there is a heavily doped semiconductor, the penetration will be very small towards heavily doped and more towards lightly doped. For explanation purpose, I am drawing approximately same. So negative ions this side, positive ions this side, right? So this formed a depletion region, that we know, yes or no? And this is N region from here to here, and this is the emitter region, or we can say P plus, right? And this is a collector region, or we can draw up to here also. right? This is N region, and this is the P plus region, emitter, base, and this will be collector. So that means what happens whenever negative charge and positive charge accumulates, so we can which will be generated, that we have seen, an electric field will be induced. The remaining will be same. So you should write something like this: holes, less number of electrons. Here holes. We will discuss about this PN junction later, right? We are just discussing about this PN junction. So whenever there is a negative charge and positive charge, an electric field will be induced. The direction from N to P, that also we have seen. From positive to negative side, there will be an electric field. Whenever there is an electric field, potential will be developed. So that potential will be called as built-in potential. That we have seen also, built-in potential or junction potential. Now can you tell what is the junction potential formula from the PN junction diode concept? V0 is equal to Vt into Ln NA by Ni square. And remember this, here we are talking about emitter base junction. We can give a different name like VO, built-in potential, under open circuit. So VOE, right? So what is Na? Na is the doping concentration in the emitter region. Nd is the doping concentration in the N region. Ni we know, intrinsic carrier concentration. And we know what is Vt? Thermal voltage. Na is the acceptor concentration in emitter region, Nd is the donor concentration in the base region, Ni is the intrinsic carrier concentration. What is thermal voltage? 25 millivolts at 300 degree Kelvin, or sometimes we will take 26 millivolts at 300 degree Kelvin. Now you may think, why I am telling this? There will be some questions based on this concept. What is the built-in potential in emitter base junction of a transistor? In the GATE exam you may find one question like this, right? So depending on this carrier concentration, they may give the carrier concentration of emitter region, base region, collector region. So that's why we can that's how we can find the built-in potential. So I hope it is clear. So when we take a P plus N junction, when we don't apply anything, diffusion will take place and there will be a depletion region will be formed. What is the depletion region width? Or we can say this will form a space charge region. And what is the width of this? W, right? We can give WE also, depletion area width of emitter base junction. So don't confuse emitter base junction depletion layer width. And this is the emitter base junction built-in potential. This will be emitter base junction electric field when we don't apply anything. So if you are having any doubt, please post a comment. See, we should understand each and every concept in NPN transistor or PNP transistor. So that's why I am going very slow. By first we are seeing open circuited PNP transistor, right? So I think it is clear how to find the built-in potential of a transistor if it is a PNP emitter base junction built-in potential, right? And we know electric field formulas also. So you can go back and see whatever the formulas applied for PN junction, the same formulas, concepts can be applied to the emitter base junction, similarly collector base junction, right? Then we will see this NP junction also. Still it is under open circuit only. We are not applying any external voltage. So what happens? Again same. Here holes are majority, here electrons are majority. So they will diffuse from P to N and N to P. So again for explanation purpose we need to draw something like this. So again I am drawing PNP only. So there is already one depletion region here and there will be one more depletion region, okay? PNP, base collector emitter, right? So minus plus minus plus minus plus. But here electron will lose, so it will become plus here. Plus here it accepting the electrons, it will become minus. So here electric field direction was, this will be P plus from N to P. Similarly, what will be the electric field direction here from N to P, right? If you are confused with the electric field direction, go back in PN junction under open circuit condition, always from plus to minus the direction of electric field. So that's why in this collector base junction the electric field direction will be from N to P. So that is the reason, suppose when we inject some holes in this region, in this depletion region, so electric field direction is like this. So this electric field push those holes towards P side collector. So collected by the collectors, holes will be collected by the collector when we inject. So how to inject holes? Using this P plus N junction. When we make this P plus N junction forward bias, holes will diffuse from P plus to N region. So these holes will be swept by this electric field towards collector side. Anyway, that we'll see when we discuss the transistor in active mode. So this is the electric field directions about this P plus N junction and this PN junction. And what is the built-in polarity here? This is plus minus V naught E, and this will be plus minus V naught, I am giving as C. So built-in potential for collector base junction, right? So remaining as it is, I am not drawing because we may confuse. So we have written for V naught E already, this is the built-in potential. So if I write V naught C, again the same formula, ln Na Nd by Ni square. But we know that this will be moderately doped, this will be lightly doped, this will be heavily doped. So that's why the built-in potential here may be large, because Na is large and Nd will be there. But here this Na we should apply, or we should substitute this region acceptor concentration. So this may be small, but for explanation purpose we can say that Na here and Na here will be same, right? So this is about the built-in potential across collector base junction. Again Vt thermal voltage. Suppose if I want to measure the depletion layer widths, so this is the again depletion layer, so width will be Wc, this is the width is We. We know the depletion layer width in a PN junction, what was the formula? 2 epsilon by Q into 1 by Na plus 1 by Nd into V naught. V naught is the built-in potential under open circuit. So if I consider W, emitter base junction, so what we should apply? 2 epsilon by Q, epsilon is the permittivity of a semiconductor, so 1 by Na, Na is the acceptor concentration for emitter, so we should substitute that value here. This is 1 by Nd into V naught E, emitter base junction built-in potential. Similarly, depletion layer width in a collector base junction, same, 2 epsilon by Q, 1 by Na, but here Na is the acceptor concentration for this collector. So you just remember that one, Nd will be same, but here V naught C. So we may get questions based on these formulas also. And we know that the We will be the penetration into the P side, penetration into the N side. So we can write as Xn naught plus Xp naught. Similarly, Wc also Xn naught plus Xp naught. And I already told, if it is heavily doped, the penetration will be less. If it is lightly doped, the penetration will be more. That means Xn naught will be smaller. If I want to find Xn naught, how to find? We know that is the total depletion layer width into opposite carrier concentration, that is Na by total carrier concentration, Na plus Nd. Similarly, Xp naught We into Nd by Na plus Nd. So here we know this is large, so Xn naught penetration to the N side will be more compared to this one. Similarly, we can go for this also, Xn naught Wc into Na by Na plus Nd. Similarly Xp naught Wc into Nd by Na plus Nd, right? And if I ask what is the electric field, so electric field will be maximum at this junction. So we can say electric field is equal to this side. So Xp naught is the width here, so minus Q by epsilon into what is the carrier concentration there, Na, into the width will be Xp naught, which can be also equal to, we can write as minus Q by epsilon into Nd into Xn naught, right? So this charge, right? So this is the electric field. Similarly we can write for this also, minus Q by epsilon into Na into Xp naught is equal to minus Q by epsilon into Nd into Xn. What we should remember is, this is for emitter base junction, this is for collector base junction, right? So this is for emitter base junction, this is for collector base junction, electric field, right? So should be very clarity on these values, so don't confuse. What are the formulas we used for PN junction? Same formulas we can apply, but we should see that emitter region will be heavily doped, this one will be lightly doped, this one will be moderately doped. So we need to substitute these concentration values only. Next we will see this potential, built-in potential, how it will be. So anyway, that we have seen already. Suppose this is emitter junction, this is the collector junction. So this is a P type and this is a N type. So there is a potential, built-in potential is there, like a barrier, right? And at this junction also there is a barrier. So this is N type base, and this is the V0E, and this will be the V0C. So for explanation purpose we can assume that the concentrations will be same, that means the barrier potential will be same, right? So this is P type collector, this is P type emitter, right? So actually here the built-in potential should be small, because here the concentration will be smaller compared to this, but explanation purpose we can assume that Na emitter is equal to Na collector. Anyway base is same. So this is the potential, this is at emitter base junction, this is at collector base junction. Similarly, when I want minority carrier concentration distributions, so we know, if I take again PNP transistor, P plus NP, this is emitter, base, collector. So who are the majority carriers here? Holes. So I am considering P suffix P, holes in P type semiconductor. So electrons will be minority, so NP. So electrons in P type semiconductor. Here who will be majority? Electrons, so N suffix N. Who will be minority? P suffix N. So again here my majority will be holes, minority will be electrons. So P suffixes are semiconductor. P means here holes, P means P type semiconductor, N means electrons, P means P type semiconductor. So electrons in P type semiconductor, electrons in N type semiconductor, holes in N type semiconductor. This is also same for this emitter and collector. So holes in P type, electrons in P type. So when we draw in a graph, so that will be something like this. So P type emitter, this is N type base, again P type collector. With distance we can draw. Suppose this is the emitter junction and this is the collector junction, right? This is the minority carrier concentration, and this can be with respect to the distance. So how to represent the minority carrier? So electrons in P type. So Suppose this is some number of electrons are there, so I am considering this is NP naught. So thermal equilibrium concentration of electrons in p side, right? So we can give different color. So this is for NP naught. We can give different heights because this is n-type base, so it is very lightly doped. We may have now very small hole concentration in this n-type base region or large compared to this also, right? Suppose if I am drawing something like this, so this is the P holes in n-type base at thermal equilibrium, right? And the similar, so who will be minority in p-type collector? Electrons. So we can have different number of electrons n p naught. So compared to this, sometimes for explanation purpose we can take same level, but compared to here, what is the minority carrier concentration formula? We know Ni square by N A, because we need electrons. So we know acceptor concentration are very large, so Ni square by Na, so this is a large quantity, so we will get very small, right? And here Ni square by Nd, we need holes, so Nd is very small, so we can get more number of holes in this compared to this, right? And similarly compared to this and this, we will get here large, because Na will be small here because moderately doped, here Na will be large. So we can have this height somewhat large compared to this, or for explanation purpose we can take same also. So this is minority carrier concentration in p side, that is electrons in collector. Actually majorities are holes. So these are the heights, np naught, pn naught, np naught. So remember, this should be high. Why? We know Pn is equal to Ni square by Nd, and we said the base is lightly doped. That means this will be the number will be small. That means compared to this and this, we'll get more number of minority carriers in n-type base, that is holes. So this is the minority carrier concentration profile. I hope it is clear. If you are having note, please post a comment, right? So the same thing we can apply for NPN transistor. So you try, pause the video and try all the formulas and the concept also. So I'm going in a very quick way. Please stop the video or pause the video and try on your own. So N region, who will be there? We know electrons. So representation is something like this. Here P holes. So representation something like this. Again electrons, 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 electrons. So when we open this, what happens? So depletion region will be formed because of diffusion. So after some time, diagram will become. So I'm going for 2 junctions at a time. So this will be the depletion region will be formed, and here one more diffusion will be formed, something like this. Collector N, P, N plus, emitter, base, collector. So N side, it will become positive ion. Here P side negative ion. Here P side negative ion. Here N side positive ion. So depletion region and built-in potential plus minus V naught. Here plus minus V naught. And what is the electric field direction? From, can you guess? From N to P, or plus charge to negative charge. So electric field direction will be like this. Here electric field direction will be something like this, right? And the same formulas can be applied. So V naught is Vt ln Na Nd by Ni square and so on. E. Similarly V naught C, right? So electric field same, depletion area width will be same, but concentration will be different. So suppose if I say WE, it will become Xn0 plus Xp0. So that penetration will be, N side will be small compared to the P side. So Xn0 will be very small compared to Xp0. So this side Xn0, this side Xp0, no, this will be large compared to this one, right? And remaining you can apply. So if I want Xn0, so WE into opposite, say N means we will get Na by Na plus Nd. Xp0 WE into Nd by Na plus Nd. So we know donor concentration in an emitter will be high, so this will be high. So penetration into the P side will be more. So remaining concept as it is we can apply. And the final conclusion is, whenever we don't apply any voltage, external voltage, we know P plus NP, PNP transistor, is there any current flows? No. Initially there will be diffusion. Due to electric field, drift current will flow. So diffusion current will be opposed by drift current. So what are the currents? Currents will be zero. Suppose this is emitter, base, collector. When we don't apply, so depletion regions will be formed, and due to this electric field will be generated. So due to this electric field, the diffusion will be stopped, or electric field is opposing the diffusion. So what are the currents? So I am giving, see, P to N, holes will moving like this, so current direction is IE. So holes are moving like this, this is current IC, right? So if it is coming like this, so obviously current of base will be going out, but anyway we'll see why it is going out also. So IE, IB, IC all are zero currents. So there is no current flow. That is the meaning, right? So this is about the open circuited transistor. So when we don't apply, depletion regions will be formed, electric field will be induced, so diffusion will be opposed by the drift, so no current will flow, and there will be some depletion regions and the built-in potentials. We can find them by using the PN junction formulas. Whatever we have derived for PN junction, same formulas we can apply for this also. And we should remember all these formulas when we want to find, suppose magnetic carriers in emitter region, we can apply this formula, right? So if I want a built-in potential in emitter base junction, we can use this formula. If someone asks you what is the electric field at the junction, and with that we are already find electric field at the junction will be maximum, so that will become minus Q by epsilon into Na, accepted concentration, into the penetration into the P side, that is a width, or minus Q by epsilon Nd into Xn0. You can apply for emitter base junction or collector base junction, right? Same formula. So I hope it is clear. If you are hanging out, please post a comment. So next we will see PN junction under active mode, right, or transistor in active mode. So that we need a lot of discussion, so that we'll see in the next lecture.